Share. So I hope you guys can see.
Yes.
I hope you are seeing just a slide, or are you just?
We see the
So,
slide in presentation mode, so that's fine, I think.
Okay, so
yeah.
I'll get started. So good evening and good afternoon to all of you. So me and Tanup are going to be presenting on terawatt attosecond hard X-ray free electron laser at high repetition rate, which can be found in the given description. So yeah, to get started, we have the Holy Trinity. We have hard X-ray in attosecond, sub-attosecond range, and terawatt peak power. That is all discussed in the same. So the goal is motivated by the fact that fundamental processes in matter are governed by simultaneously small length scales and extremely fast time scale. When you come to the spatial side, atomic spacings and core electronic orbitals are on the order of angstrom, whereas hard X-rays of in the energies of around 9 kilo electron volts have the wavelengths of approximately 1.4 angstrom, which means they are naturally suited for probing matters at the atomic scale, including element-specific core-level dynamics. When you come to the temporal side, which is purely electronic processes such as electronic motion and charge migration occurs in the time scales of 10 to hundreds of attosecond. Even after X-ray absorption, core hole lifetimes are only a few femtoseconds, and subsequent Auger decay cascades occur within 1 to 10 femtoseconds. To directly observe these processes, the probe pulse must be comparable or shorter than this intrinsic timescale. Conventional femtosecond X-ray pulses are therefore fundamentally insufficient for resolving such ultra-fast electronic dynamics. In addition to ultra-short duration, extremely high peak power is required. Attosecond pulses contain only a very small number of photons unless the peak power is increased to the terawatt level. Such high photon density is essential in doing single shot measurements, single particle diffraction, and nonlinear X-ray matter interaction. So therefore, all these challenges are addressed in this paper. So moving on to slide 2. Before discussing like how attosecond hard X-ray pulses are generated, let's see the fundamental limitations of the standard XFEL operation. So conventionally, like XFELs typically operate in the SASE mode. In this mode, the generated X-ray pulses have durations in the range of about 10 to 50 femtoseconds and peak powers on the order of gigawatts. So the key issue is that femtosecond X-ray pulses already significantly damage the electronic structure of the sample during the measurement itself. When an intense X-ray pulse interacts with the matter, the core electrons are photoionized, which producing high energy photoelectrons. These are then followed by Auger decay processes, which release additional electrons. Together, these electrons initiate collisional ionization cascades within the sample. So these cascades actually evolve on femtosecond timescale and rapidly modify the electronic configuration. So as a result, when we do a femtosecond XFEL pulse, the structure that is being probed is already changing. The measured diffraction signal becomes a time average mixture of damaged and undamaged states. As I think we saw in the previous lecture, we mentioned something about diffraction before destruction. So standard femtosecond XCFL pulses are in many cases still too long to truly capture the pristine electronic structure. So to genuinely like outrun these damage processes, so we should have the X-ray pulse duration much shorter than the electron cascade time scale, so that scattering occurs before significant redistribution of charge takes place. So this naturally pushes from the femtosecond regime to the attosecond regime. So moving on to the slide number 3. So whenever we think about attosecond pulses, what is our like standard method? We say like HHG can routinely produce attosecond duration. So it has its own success in strong field physics, but when you come to photon energies and usable photon flux, we see HHG lacking. In terms of photon energy, most HEG sources operate in XUV range. Although like the photon energies can go up to kilo electron volt, extending it to hard X-ray regime remains extremely challenging. So more importantly, the pulse energy of HEG is typically in the picojoule to nanojoule range, corresponding only about 10 to the power 6 to 10 to the power 8 photons per pulse. So for applications such as single particle imaging or nonlinear X-ray matter interaction, this photon number is far below what is required. This typically demands for us to have around 10 power 11 or 10 power 12 photon pulse and focused to per square millimeter around 10 power 20. So the maximum harmonic photon energy is governed by this cutoff law, which is given by the sum of the ionization potential of the atom and approximately 3.17 times the Ponder motive energy. Since the Ponder motive energy scales with the laser intensity and the square of the wavelength, extending the cutoff to higher photon energy requires both very high intensity and long wavelength driving lasers. So this comes at a severe cost. The conversion efficiency of HHG drops dramatically with increasing harmonic order and longer wavelengths, often falling below 10 to minus 6. As a consequence, even though higher photon energies can be reached in principle, the resulting pulse energy remains far below 1 microjoule, which is demanding for hard X-ray experiments. While HAG can excel at isolated attosecond pulses, it cannot deliver us simultaneously hard X-ray photons with high photon flux. So moving on to slide 4. So to understand, to understand both the strengths and limitations of standard XFEL, we need to first understand how there's radiation generated in the SASE mode. So SASE stands for self-amplification of spontaneous emission. So it starts from the fact that electron bunch entering the undulator has no initial phase coherence. The electrons are randomly distributed along the bunch, and the radiation initially originates from microscopic short noise. As the electrons propagate through the undulator, each electron emits a spontaneous undulator radiation. The radiation then co-propagates with the electron bunch and interacts back with it to the transverse electric field. This interaction causes a longitudinal energy modulation of the electrons, which are then converted into density modulation as electronic slip relative to the radiation field. This was also discussed by the first General Club session, which was done by Vishwas and team. So as a result, the initial smooth electron bunch breaks up into a series of density spikes by one radiation wavelength. This process is known as microbunching. You can see this clearly in the phase space plot shown here. After a short undulator wavelength, electron distribution is still mostly random. As the undulator length increases, periodic density modulations develop, and eventually well-defined microbunches appear on the scale, which is on the scale of the resonant wavelength. Once microbunching is established, electrons within each microbunch emit radiation in phase. This leads to coherent emission, and the radiated power grows exponentially. I think there was an equation which says like when they are in phase, it happens in the square of the intensity is in the square of the number of electrons. So this plot on the right shows this exponential growth of pulse energy as a function of undulator length until saturation is reached. However, because SASE starts from short noise, the process is intrinsically stochastic. Each microbunch emits independently, leading to strong pulse-to-pulse fluctuation and limited temporal coherence and a spiky temporal and spectral structure. So moving on to slide 5 and 6. So we have discussed how SASE works conceptually. So the key point is that XFEL radiation relies on extremely high electron density inside the undulator. This high density is what enables a very strong coupling between the electron beam and the radiation field. As a result, the undulator radiation intensity becomes extremely high, reaching values of in the next slide. Now, yeah, reaching in the orders of 10 to the power 10 watts per square centimeter or higher. At such intensity, co-propagating radiation field is strong enough to significantly modulate the electron energy and density, which is essential for us to maintain this exponential field amplification along the undulator. To achieve this regime, we have some several like conditions that must be satisfied simultaneously. The electron beam energy must be very high, typically on the range of several giga electron volts, which will then travel into, translates into high radiated X-ray power. Second, the beam must be transversely very small, with spot sizes on the order of 10 micrometers in order to maintain high current density and strong overlap with the radiation field. Third, the electron bunch must be short, typically corresponding to pulse duration of few tens of femtosecond, so that high peak current can be achieved. In addition, the undulator must be long, often tens of meters, to allow sufficient interaction length. And then we have like precision up to like a few micrometers that will be allowed. Yeah. So moving to the next slide. Now I'll explain like how electrons actually interact with the light inside an undulator. Inside the undulator, the electron does not move straight. It oscillates transversely due to the magnetic field. At the same time, an electromagnetic wave propagates along the same direction. For the electron to continuously exchange energy with this wave, it must stay synchronized with it as both travel through the undulator. If the electron slips too fast or slow with respect to the light wave, then the throughout the sine wave of it, like the acceleration that is done, it will be decelerated along the wave. So requiring that electrons sees the same phase of electromagnetic wave after each undulator period leads directly to this undulator resonance condition. So this resonance condition tells us which radiation wavelength is emitted for a given undulator period, electron energy, and magnetic field strength. Physically, it means that during one undulator period, the electron slips forward by exactly one radiation wavelength relative to the light. Once this resonance condition is satisfied, energy exchange between the electron and radiation becomes possible. However, if the electron gains or loses energy, it depends on the phase. So that's what we are seeing in the three sketches. In the first case, the electron is exactly in phase with the light field. The accelerating and decelerating forces cancel over one oscillation, so there is no net energy exchange. In the second phase, the electron enters the wave at a phase of plus pi by 2. In this situation, the electron consistently loses energy to the radiation field, which corresponds to the amplification of light. In the third case, the electron enters minus pi by 2. Here, the electron gains energy from the light field and is accelerated instead. So in an XFEL, electrons that lose energy remain in resonance and reinforce the radiation field, while the electrons that gain energy fall out of resonance. So this phase-dependent interaction is the fundamental mechanism that leads to the energy modulation, microbunching, and eventually coherent X-ray emission. So moving on to the next slide. So here we'll speak about how bunching happens, and yeah. So at the exit of the injector and the first linac, the electron bunch is relatively long in time, typically on the order of tens of picosecond, and the peak current is correspondingly low. In this stage, the RF field of the linac is used not only to accelerate the beam, but also produce a control energy chip along the bunch. This means the electrons at the head and the tail bunch have slightly different energies. The bunch then passes to the magnetic bunch compressor, which is essentially a dispersive section where high energy electrons take a shorter path and the low energy electrons take a longer path. Because of this energy dependent path length, the longitudinal positions of the electron shift and the bunch is compressed in time. This process can be clearly understood by this longitudinal phase space. Initially, the bunch has a small energy spread and a long temporal extent. After the Linac, the energy chirp tilts the phase space distribution. After the bunch compressor, this tilted distribution is rotated, resulting in a much shorter bunch length and a dramatically increased peak current. As shown here, peak currents increase from a few tens of amperes for long bunches to well above 1 kiloampere for bunch lengths of order of few tens of femtosecond. This high peak current is essential for driving the and achieving strong radiation amplification in undulator. So in the we can move to the next slide. Yeah. So now I'm going to explain what chirping means. So in a conventional accelerator, an energy chirp means a smooth correlation between longitudinal position and energy along the electron bunch. Typically, the head, center, and tail bunch differ slightly in energy with the linearly slope introduced intentionally by off-crest RF acceleration. This chirp is usually weak and distributed over the entire bunch. Now, what in this paper they do is, this is the main point, they do something called extreme chirping. So in this experiment, the beam is compressed to such a high peak current that the chirp is no longer like a gentle global effect. Instead, it's a very short fraction of the bunch experiences an extremely steep energy gradient, and the energy changes dramatically over a few femtoseconds rather than gradually over the bunch. So what happens to this head, center, and tail? So after strong compression, the current distribution becomes highly asymmetric. The head of the bunch carries the highest current density, while the tail is relatively dilute. As the bunch propagates, the head interacts first with the accelerator structure, leaving behind electromagnetic field that persists in time. These fields then act back on the center and tail of the bunch. This is like the main concept that the author is trying to bring about in the paper. So there are self-generated electromagnetic fields which are created called wake fields. They're produced because the electron bunch does not travel through free space, but they are traveling through RF cavities, vacuum chamber, and beamline components. They have finite conductivity. So when an high current bunch passes through this structure, it excites electromagnetic modes in the surrounding material. These modes do not vanish instantly. They trail behind the bunch, much like the waves that are left behind a boat. So speaking about the interaction with the RF cavities, in RF cavity, this effect is especially strong because the cavity supports resonant electromagnetic modes. The ultra short, high charge bunch excites longitudinal wake modes that produce decelerating, accelerating fields behind the head of the bunch. As a result, the head of the bunch loses relatively little energy, while the center and tail experiences the strong additional energy loss that's created by the wake field. So this will create a sharp localized energy drop along the bunch. Under normal operating conditions, these wake fields are weak and can be treated as some small perturbations. However, when the bunch is extremely compressed, the peak current becomes very large, and the wake field strength actually scales directly with this current. At the same time, the bunch length becomes comparable to the characteristic wavelength of the cavity wake. This makes this wake field interaction highly nonlinear and strongly localized in time. This kind of creates a positive feedback loop. So once a localized energy chirp starts to form, it further enhances the wake field interaction. A steeper chirp leads to a stronger current spike, which in turn excites stronger wake fields. So physically, the being creates its own RF environment. The head of the bunch excites electromagnetic fields in the accelerator structure, and the fields of the and these fields act back on the rest of the bunch. So this is called as the selective, like an over chirping at a very small temporal scale. So what it also does is, in addition to this wake fields, another important collective effect takes place, that is coherent radiation. When the bunch length becomes comparable or shorter than the emitted radiation wavelength, the radiation formed from individual electrons act coherently rather than incoherently. In this regime, the radiated power scales with the square of the number of electrons rather than linearly. So moving on, like the combined effect of wake fields and this coherent radiation reshapes the longitudinal phase space in a self-consisting way. The beam not only experiences external RF field but also interacts strongly with its own self-generated electron field. This collective interaction is what makes the chirping in this experimental fundamentally different from the conventional externally imposed chirps by the RF field. So when you come to panel A, you can see that due to the chirping, the head, so left side comes as for the head of the bunch. It's more of like you can say a short frame of the this of an electron bunch. So you can see most of the electrons are localized in the left corner, having about 10 kiloampere. And due to the chirping, like if it is normal chirping, it will be the delta E curve should be some linear curve where the tail gets higher energy so that it can catch up and the head will get lower energy so it moves back. So after it passes through the bunch compressor, basically this A diagram is what you see after the BC2. So like in panel B, what you have seen is it passes through the collimator and you can see the delta E has a drop. Its delta E is basically like with reference to one particular reference electron. So you can see drop right after the head. That means it has experienced a wake field. And through the collimator, like most of the unrequired electrons are the energy scales that are not required to us will be cut off. And you can see it has also been the electron beam has been accelerated up to 16.2 giga electron volts, which is after L3 and the collimator. When you come to the panel C, you see that compression, it has passed through the compression arc. What this compression arc does is it gives a transverse kick. So whatever like extra peaks or supplementary peaks that are not required are made to pass in its normal path, whereas rest of them, the ones that are required, like it depends on this factor called R56, where uh, higher energy ones get shorter path difference, and then higher energy terms get like higher energy gets shorter and lower energy gets longer path. Yeah. So then, due to the compression arc, you see that it gets a transverse kick, and uh, it has reached to like a small femtosecond ledge, I mean region, and all the electrons are compressed in that region with varying energy. So you can see that the current has gone up to like 40 kiloamperes. And finally, it passes to the undulator, where you see only this particular energy spike being amplified into what is required to us, that is 1 terawatt of power in sub-femtosecond range. And you can see this is the diagram E is a 9 kilo electron volt pulse, which has about 16 electron volts of FWMH. And you can see the intensity, most of the electrons are in that range with very minimal dispersion. So next, the results part will be continued by Tanu.
Yeah. So now that we got to know how it's done, why it's done, and why we have to do it, let's get to the what has been done through the results. So the experiment was first of all conducted in the SAS2 undulator line of the European XFEL, which utilized a 250 picocoulomb and energy of 16.2 giga electron volt electron beam. The SAS2 contains 35 undulator cells, and this is why a fact about European XFEL is that it is one of the largest X-ray free electron lasers. So, going to the results. So this basically the paper has three images or panels of results. So the first one is showing the first panel basically mentions how well the electron beam is getting properly spiked or perhaps like becoming shorter and shorter. So if you see, panels A, B, and C are from a regular run in European FEL at 9 kilo keV. Uh, so panel A, B, D, E, G, E is uh, basically 100 consecutive measurements and single representative spectrum of the FEL pulse generated. First, AB is for the regular run. DE is for after self-stir without an arc compression. And finally, GH is with the arc compression. So, and then C, F, and I are the spikes, a histogram of the number of spikes found within each run. So spikes are like, if you see this delta E versus, wait, one second. Yeah. Can you see my pen in the screen?
Yes, yes, it's good.
So the spikes are each of these spikes, which when they took around 100 consecutive measurements, they plotted the histogram with respect to the fractions. It was on an average, the spike was 20. When it was compared to after the self-check without an arc compression, it was 4. And finally, when with the arc compression, it was majorly peaking around 2. So, so this is what in a typical SAS run, they found it was having approximately 20 spikes and a mean energy of 2170 microjoules, while after self-chirping process without any arc compression, it went down to 4 spikes and with an energy of 124 microjoules spread across the 4 spikes. Whereas when we got it down to just 2 spikes when they got it down to 2 spikes using an arc compressor, the energy or we got a higher energy locally around 174 microjoules, which is the huge first thing which Anutam had told, the high power. This we can clearly see that there is a higher power. Now the second panel basically shows the analysis of 1044 single spike spectra out of 3500 total consecutive spectra. So these were each and every time they took the spectra of a single spike event and analyzed it. It usually that's what is shown in panel A with spectral density versus delta E. So from that, they plotted another histogram with the pulse energy versus the number of events and found the mean energy to be 184 microjoules with a standard deviation of 22 microjoules. With an observation of that, 90% of the pulses exceeded the energy of 150 microjoules. Oh, sorry for the typo. Uh, so after that, they measured the bandwidth uh, to find the pulse width of the generated X-rays, you have to find the bandwidth, after which it can be converted into the Fourier limited domain, after which when you can convert it back to your regular domain. When this was done, sorry, it was found out the pulses had a bandwidth of 13.8 plus or minus 3.4 electron volts from the histogram they had plotted. And from that, they were able to get it in the Fourier limit domain, the full width half maxima duration as 139 plus or minus 37 attoseconds. And to convert it into the regular domain, you have to divide it by a root 2 factor or multiply it by a root 2 factor. So with that, it was found out 197 plus or minus 52 attosecond is the duration of a single spiked event with a average power around 0.9 tetrawatts, which in a way is not an tetrawatt, but they have reached zero point 0.9 tetrawatt. So the final panel in this, the D panel just shows the uh, each of the events they had recorded pulse width with respect to the pulse energy, and it can be clearly noted it is bunched up in this particular region, which is a good thing for as far as I can understand. So now the final panel talks about the first point, the repetition rate here. For this, what they had done is, when they measured, there were each train comprising of 200 electron bunches at an train rep rate of around 2.25 megahertz, corresponding a continuous average rate of 2 kilohertz. So then they measured every four pulse coming into the took the single shot spectrogram spectrometer samples were sampled at four spectra every fourth pulse, giving them approximately 60 spectra per train. So in this, the pulse energy across 100 trains with an average was measured around 159 plus or minus 26 microjoules, which is shown in panel B, and it is relatively stable across the train. Uh, and on panel A shows each one of the trains spectral data which they had recorded. And panel C shows the bandwidth of each single cycle event. Sorry for that. So from that they found it out to be 13.3 plus or minus 3.6 electron volt, which corresponded to an 207 plus or minus 62 attoseconds. When they analyzed this, they found out one more thing. When the spectral analysis of 50,000 pulses spanning across 1,000 trains were done, it was noted that 15% of the spectra are single spikes, and rest 37 and another 37 exhibited a two spike structure, which has been commented in the paper where like this. I'm taking this directly from the paper. The average number of spectra spikes increased from 2.05 to 2.51. The observed increase in average spatial spikes is primarily attributed to the imperfect trajectory corresponding reaction along the pulse train. So they are explaining this increase in average spike by telling that there could be a deviation in the electron bunching. No, the pulse trajectory imperfections across the train. So coming to the results part, they were in a gist. The resulting single spike XFEL pulses had an average duration of 200 attosecond level and an average pulse energy of 184 microjoules, which when compared to a standard HHG experiment is or any a standard XFEL operation is very much very good because you are getting peak power of tetrawatts, hard X-ray of 9 keV, and a pulse width of 100 attoseconds. That's all from my side. Thank you.
Yeah, thank you very much. I think this was quite some tremendous work. I mean, definitely you looked through the paper very thoroughly and did a very good job in presenting all the fine details, which I honestly did not fully get about. I mean, I was very impressed that you like figured out about this wake field effects. Which is yeah, not definitely non-trivial, but well done. Are there any
I
questions?
actually had spoken to the author of the paper to completely understand it. So I had
Okay.
contacted him via LinkedIn and asked, like, what exactly are we trying to? So he gave me an idea. It's something like the wake key.
Okay, okay, wow. Yes, yeah, because I mean, looking at the paper, it was rather brief and I think not really possible to get
Yeah.
all the details out. But I mean, that's impressive. Thank you very much. It very interesting to now really like learn and understand. I mean, it sounds a bit similar to this leap X-leap mode, where also I think the in the LCLS FEL, where also the electron bunch induces in the wiggler some strong infrared field, which then back couples and like reshapes the electron bunch, right? It is always this, anyway, it's always this back and forth interaction between the electron bunch and the radiation that it emits. But in your case, I think the difference was probably that there's even this coupling to the cavity, which then
Yes. The head of the bunch basically interacts with RF cavities and
yeah, that's really I think that's a very, very new aspect that that probably never really plays a role, because the like electron beam current or the electron density is usually never high enough to induce such effects, I assume, right? So that's is probably the new physics that comes into the play at European XFEL, due to these enormous, like, multi-kilo electron, no, kilo ampere uh, electron currents, right? This is very, very impressive. Yeah, I mean, thanks for digging so deeply into this XFEL physics. Are there any more questions or comments from the audience? And what I did not fully get, maybe I just didn't pay attention, this arc compressor. Could you did you mention how it works, or what it is, or
uh,
maybe I just missed
So,
it?
Professor, so the R compressor initially was placed to redirect the beam initially in the normal operations, like between different undulator lines, which then later they had used it in a P54 config. One sec. Yeah, in the arc session, like it was used in for its longitudinal dispersion strength was controlled by turning and quadrupole inside. So it was operated in an R56 configuration to compress the beam. It was initially used to redirect between different undulator lines.
Mm-hmm.
And do you have anything you were saying?
yeah, that's about it. It helps us
Yeah.
to select what we want to like gets transfers like into the whole the required attosecond slicing, and the ones we don't want are just uh, don't get that transfer speed. So somewhat like that. There's this equation like R56 into like it varies the path length based on the energies. So
Mm-hmm.
it's more or less like a bunch compressor, but this has a particular shape to get it all together.
Okay. So, did you, just out of curiosity, do you think, or did you find out whether this whole scheme of creating these extremely short bunches and pulses, was it like planned like this? Did they like do simulations and then tweak the machine accordingly, or was it more trial and error, and by chance
Uh,
finding out that it works in such a mode?
I actually did not ask that. Maybe in our future conversation.
Okay.
Like I
Yeah, I
just asked in the
feel
morning, like I had studied upon it that it must be something like the Wakefield, so I just wanted to confirm. So
so like, but in this paper, it has mentioned they have done some simulation works, and also like in the results section, they have given out that they are the 44 single spectra was out of 3,500 was done to optimize the way the output was there. So I think they had done a mix of like simulating a bunch and then tweaking around and optimizing by taking different readings.
Mm-hmm. Yeah, it's just a question. Did they first find this like interesting behavior of the beam, and then do simulations afterwards to like understand and further optimize, or was it like a concept thought out from the beginning and then converted into the experimental scheme? But in the end, it doesn't matter. It's I think the point is there's so many knobs on these complicated machines that you can tweak, that
Yeah.
it is very hard to I guess, to do this in a very deterministic and predictable way, because it's such a multi-parameter system, and all the many parameters depend or have a nonlinear effect on the outcome, because this whole amplification is a highly nonlinear process. But it's impressive that you can reach these conditions. So yeah, thank you for really digging so deep into it.
Thank you.
Thank you, Professor.
Anuttam, who was the author who spoke?
I can't pronounce his name. I think it's in the first slide. Tanu, just could you put it up?
I'm just curious. Jiawei Yang.
Yan.
Oh,
Sounds Korean / Chinese.
it's Chinese, I think.
Yeah, he's Chinese.
I think he's a quite young guy, isn't he? I think he was he got even a, a prize for his work, like young researcher award that is every year European XFEL awards a young researcher for excellent work, and I think he got that prize this time. So there's always need and opportunities for excellent young researchers to contribute to these kind of studies. Yeah. Okay. Yeah. Thanks a lot. Are there any further questions, comments? And we have had already another very nice presentation about then really an experiment that was done using two attosecond pulses to actually, which also was very impressive because it demonstrated that these attosecond pulses are not just interesting for their own merit to see how far the limits can be pushed, but they can actually be used for resolving important questions in science. So that was another nice presentation that we have had. And certainly this type of work will be now extended very intensely, because this is at the frontier of this type of research, and opens up so many opportunities to study electron dynamics, to study ultra-fast processes in solid state, like ultra-fast relaxation in solid state systems and so on. So we will certainly hear much more about, or in other words, finally, the Attosecond community starts to deliver. This is like
after the Nobel Prize, as usual.
Yes, and after many decades of loud promises of like revolutionizing ultra-fast physics and so on, and so far, I would say we have not seen so many like very convincing applications of attosecond pulses, but now, probably due to the fact that these pulses like are terawatt and like were really intense enough to drive processes and also come at a high repetition rate, that we will certainly see many more applications now also coming up. So I thought we would have another presentation today on the topic of coherent diffraction imaging. That was originally the plan. Actually, originally it was planned to have two, but one was already canceled, and it seems the other author or the other student, Nishta, is not there today. Or is Nishta there?
Who?
So this was actually, I just looked through my emails. I did try to contact Nishta, and then
Nishta, okay. Marcel, I will contact her about maybe she also took the holiday.
Yeah, it's Nishta Lakhanpal.
Okay, yeah.
I think so. She had chosen the publication by Alessandro Colombo on this coherent diffraction imaging, but it seems that it didn't work out for her today. But I think that's fine. We have had this really excellent presentation and already many other talks. So then I think that's it for today. If nobody else wants to step in, I guess not. I won't. I have done my things. And last time I have already shown quite a number of examples of what kind of X-ray diffraction imaging you can do with XFEL. So I think you have gotten a good idea already. Then just let me announce that tomorrow will be the last session in this course, and this will be a tutorial again using